came into class, you saw the tests laid out over here, and hopefully you've picked them up. If not, come get them. Let's look at the test real quick. As you know, we did a test a week ago. It was a half test. Remember this, if you see your score, it's out of 60, so don't panic. If you see something like a 51, that's actually 85%, and that's a good score. It's not 51%. I thought about that when I sent you the email link. I hope that you got the email link and you were able to check it. I think I sent it late Saturday night, so if you got a moment to look at it, you could have checked your grades. If not, doesn't matter. You can check it today here, but you'll do want to check your pipeline account. It does have that link, and so as the semester goes along, and particularly at the end of the semester, you're definitely going to want to click on that link and see what your scores are and your grades are and all that good stuff there. All right. Also, wanted to point out we've got some activity this week for our department that affects this class. I mentioned it before. It's worth mentioning it again. I'll grab the syllabus real quick before we go over the test and just kind of mention it. The first one is on the syllabus. It's very clear. I mentioned before that our department was going through a hiring time, and it's a busy time, but a very important time, and one that should have been done 10 years ago and wasn't, so glad we're able to do it now. But it down here, where am I getting at? This week in the lab, there is no lab this week for just that reason. We're going to tie up that room down there, PS 116, and both Don and I will be in there most of the day Thursday and all day Friday doing interviews. And the reason I say it affects your class is because obviously we can't do the lab on Thursday, so I knew that starting the semester. That's why I scheduled it. What I didn't know starting the semester is that we needed that room to do the interview. So that also means the MC is canceled for this week. So there's no Friday MC, and I think I mentioned that one time already too when Don came in during the holiday for that. And in part of that anticipation, I'm going to say then, as far as the homework, do what you can, do the best that you can, but if you don't finish this week's homework, which is chapter 20, which we're about to start by next Tuesday, completely understandable, not a concern to me. I also am going to have to cut class halfway on Thursday. So again, as I mentioned, Thursday's class is only going to be from 9 or 8:55 to 10 o'clock, and then we'll stop at 10 o'clock. So again, that's going to cut us a little short, and because of that, I may not get a chance to do too many examples from chapter 20. And that's fine. We'll just make that flow into Tuesday. So it might put us a little behind the schedule, but like I said, it's just the way we'll deal with it. A couple questions, yeah.
On Friday, will you guys be unlocking the room next to the lab? Or?
Well, all the other rooms will be unlocked. So if you're talking about the tutor room, PS 112, yes, that will be open, and you feel free to use that. Also, unlocked will be the other lab, PS 116, with the computers, and feel free to do that. But what will be closed up is the 116. That's where we'll be doing the interviews, and then some of the internal rooms too connected to that, but that won't affect you. Yeah.
Did you say we're starting on 20?
So we're going to start 20 right now.
Okay.
Yeah, as soon as we go over the test. Yeah. Yeah. All right. And so, simply put, instead of having 4 hours of lecture this week, we're going to have 3. We'll see how far we get. Probably means we'll do all the material but not example problems. So if you do what you can, and then when we come back on Tuesday, then that'll give you a chance, and to still do them. All right. Well, with that said, then let's jump over to the test. Remember, they're 20 points each, total out of 60, so see what your test score is. On average, you guys did very, very well, and so you should be praised for all that. Keep in mind that if you are doing all the labs and all the homework, to get an A, that's 90% in the class, you need to score at least 85% on the test. So that means on this test it would be around 51%. So if you scored a 51% or higher, you could put yourself in the A category for right now. So keep that up and you'll finish with an A. If you scored higher than 73%, which I'm not sure what number that is. What is 73% of 60? So around 44. So if you scored 44 or higher, you would be getting I would call it a B in class right now. And you can do the same math with the C and D and F for that matter. All right, so let's look at these three here real quick before we continue on with our thermodynamics. And this chapter, I think we start to get to things you haven't done before. I'm guessing that the stuff we just did in 19 you've all seen for the most part. Actually, for that matter, the stuff you're at the beginning of chapter 20 you've seen, but not the other half of chapter 20. But let's start with number 1. Here we've got this bullet being fired into this block of wood that's hooked to a spring. And hopefully you recognized it right away, right from chapter 15. You don't have to write out the differential equation, but if you do start, as some of you did with Newton's second law, and from there say it equals to minus kx, and from there get a second order differential equation, and from there point out that omega is the square root of the stuff in front, and from there point out that the period is 2 pi over omega. Great. But if you just remembered that omega was the square root of k over m, that's fine too. And so however you got to the period, great. I will start with the omega. We know the spring constant of this spring is 7.7 times 10 to the 3. The thing that you might want to keep in the mental picture here, here's where the physics comes in, is when it does start oscillating, the bullet is in the block. So the mass is 0.645 kilograms. That is, it is the mass of both the block and now the bullet that is embedded in it. And most of you saw that, but some of you left off the mass of the bullet, and that could give you a slightly different number there. But this gives us an omega of 109.3 inverse seconds or hertz. You put that number into our equation for the period, and you come up with 0.0575 seconds. And so it's going to be a fast oscillation here, about 20 times a second here. 20? Yeah, 20 times a second. So it makes sense. It's a real stiff spring here with a spring constant that large. Grabbing the test? Yeah, right over there. So that's A. That's the first half of it. Here's B, an extension or a continuation of that. From that, what then is the speed of the bullet? And you can go down two approaches. Some of you chose to go down the approach of conservation of energy and some of conservation of momentum. I would encourage the momentum. Be careful with the energy. Somebody was asking me about it. No, it's not wrong, but you could do it incompletely if you forget there's heat during the impact. So if you're willing to say, look, this is the initial kinetic energy, mass of the bullet times velocity of the bullet squared. As that bullet comes racing in and hits then this block, then the bullet and the, what symbol shall I use for the block? Capital M? Block are then going to be moving, and I'll put a little Q for heat there as the added piece. And that could easily be overlooked here. And I saw a lot of them that said, oops, got the heat there. So if you want to go that approach, that's fine. Just don't get it. And I guess what I'm trying to say is what a bunch of people asked me was, is using conservation of energy wrong? No, that's not wrong. Forgetting to use heat with conservation of energy is wrong. See the difference? So I want to make sure that's clear. Now, momentum is probably the best way to handle this, because we do know that the change in momentum, maybe I should write it this way from our 121, is that the change in momentum is force over a small moment in time. And so our argument was that if you have no external forces, or, and don't forget this part, if the external force is on such a small time scale, there is very little to no change in momentum. And that's what's happening here. This bullet comes racing in here, and it's going to go from a very large speed, which we don't know what it is quite yet, to a very low speed. Simply put, is that this number, I don't really know it exactly, but I can at least argue that it is small, and hence we can say it's a little bit or perhaps it's nothing. You might remember we did something like this in 121. We did a problem where there was friction on the ground, and the idea was to shoot the bullet. And we had exactly the same discussion. You shoot the bullet into here, and during that there is an external force, the force of friction. But it is so small that if you think about this as maybe an average force here, and in this case it would be a force of kx for a small moment in time, you might think of this as k over a small distance over a small time or something. And so the point here is there an external force? Yes. But how much is it small? And I'll show you in a second. It does turn out to be small. And it's exactly like we did here. We fired it here and we said, okay, we could say the momentum before is equal to the momentum after, or at least almost equal to. You could say minus a small amount, negligible amount, depending on how much distance this moved. Okay? And so let's take a moment and at least mention that, because what I was looking for, and most of you saw that, okay, it is a conservation of momentum, and so you took the mass of the bullet, 0.045 kilograms for the mass of the bullet, and you said times the velocity of the bullet must then equal 0.645, that's the mass after the impact, times the velocity, and I'll just put after the impact, and you left it there. You could have put plus or minus a small amount, and again we'll add that or subtract that depending if you want to keep that into the picture. But most of you said this is going to be small. It makes the problem very simple. Like I said, it's worth justifying that is small, but I wasn't looking for that. I wasn't trying to get you to go back to physics 121. This was just, a quick calculation. What is the velocity of the bullet? Because obviously this is chapter 15. This is chapter, 15, and this was the other piece I was after. This is chapter 15. What is the speed after the impact? And so we've done this stuff. How are we going to get the speed after the impact? And one of the things we learned is that the omega times the amplitude is the maximum speed when something is oscillating. And that's what I was after in this problem. And so we know the omega and we know the A. And so this number is the 109.3. This number is the 215. And so when you put that together, you get 23. And so what we know is the speed after the impact for sure is 23. What we're still not sure about is the speed before the impact. But if you go ahead and say, well, I'll assume it doesn't change momentum by much, you do finish the problem by saying, here then is the speed after the impact. So the speed is 333 meters per second before the impact. It's 23 after the impact. And so that's, like I said, is a same number you'd get if you included the heat, although I'm not sure you could calculate the heat without coming over here to doing the momentum. And of course, our justification that number is small, just like we did back here in 121, was simply this, that, okay, if we ignore this, we know for sure that after the impact, this is the speed. So if there was no loss in momentum, this would be the speed of the bullet. If there was a small loss in momentum. That would say the speed of the bullet is even greater than this. And when you have a speed of something going this fast, and a moment later it is going this fast, that means it's got to change from a speed here to a speed here within the size of this block. And if you want to calculate the time on it, you're going to see it's an amazingly small amount of time. And so that was our argument about fast impacts in 21. And so same thing here. Yeah. Wait. So I'm saying there really isn't a loss in momentum because there is not an external force over a period of time. Does that make sense?
Oh, you said if there was a loss in momentum, it would be small, but what would cause?
Well, this is why we have a loss in momentum. An external force. And that external force in this case would be the spring. So the bullet and the block are being pushed by the spring. And again, if this helps, coming back to 121, when we had the bullet hitting a block, the external force is the friction. And yet we still said the momentum immediately before and immediately after was the same. We only included the friction when we asked how far would this block slide before it came to a stop. And in fact, I was just working with the 121 students, so the problem I'm thinking of, it went 7.5 meters in the bullet. But our argument was during the impact, it has moved a very short distance. I mean, the time would be maybe the average speed of these two, 337 plus 23 divided by 2. Time is distance divided by velocity. So, I don't know. I'm just going to make up a number because I really didn't give a number because I didn't want you to go down there. I mean, how big is this block? 2 centimeters, 3 centimeters, 4 centimeters? But if you do that calculation, you're going to see the time is small, the force is small, because it barely moves. The spring barely compresses. The time is extremely small. And that was our whole argument, that we're not even going to worry about changing momentum. And so that's why these fast impacts, we said the momentum is before. Well, anyways, I guess I didn't mean to get bogged down into physics 121 stuff. That wasn't the main point. This, and particularly this was the main point. And that's why this mistake, I didn't make a big penalty. I didn't want to penalize you too much for forgetting that. But at the same time, I want you to remember, don't forget the heat of the impact. In fact, it might be worth no, that's more 121 stuff. But boy, if you calculate this energy before the impact, and you calculate the energy it has now, after the impact, you're going to see like over 90% of the energy is converted into heat. It's an amazing amount that's converted. You can't just ignore the heat. That's our justification. You can't ignore it, but you can't ignore the momentum. The momentum change is very, very small. The energy change is not. All right, well, I'll turn the page to the next one. Obviously, we got into sound waves here. One of the many things that we covered, and you probably noticed the same thing. Since it was only a half a test, I only had 3 problems to give you, but we covered a lot of material, or different kinds of material. So personally, I really struggled on which 3 problems to give you. I made a list of 10, and I go, oh, these would be good, but obviously I didn't want to put a test with 10 problems, even on a full test, let alone a half test there. But anyways, one of the ones I picked that I thought would be good here is with the Doppler effect here. And so this one's got all the fancy pieces of the Doppler effect. So hopefully one of the first things you did here is to realize it is a Doppler effect. And so you wrote something like this right away, saying this would be the shift in frequency. And so that's the question. What frequency does the cyclist hear? Okay? And we know this much. We know that the frequency of the whistle is 570 hertz. That's the given part of the problem. The difficult part of the problem is all these details, the plus minus, the speed of the source, the speed of the observer, the speed of the sound waves. I'll start there with the speed of the sound waves, because it does say the temperature on this cold day. It says it's a cold day of 3 degrees Celsius. So hopefully you did a 331 times the square root of 1 plus 3 over 273. Or if you did 331 plus 0.6t, whichever way you wanted to do this. I gave you both into calculating the speed of sound based upon temperature. Hopefully you recognized it right away and came up with I'll go 332.8. And so there's the speed of sound on this cold day. So much lower than the 343 that we've done by default when we didn't give the temperature. That's room temperature. But here we have the temperature here. So there would be major step number 1 well, I guess this is major step number 1, but then this is the next one saying, okay, what is that speed? But another tough piece is right here. Why don't I go with the velocity of the source? The source being the whistle itself. But here's what's interesting. The whistle here has then the wind blowing. So the whistle's just sitting there blowing, but the wind is coming by. And again, glad to see most of you got it, but you did have a homework problem like this. If you could imagine then this sound source sending out a whistle, then of course the sound would be traveling out at this speed. However, if the wind is blowing, and in this case the wind is blowing which way? To the south. So here's the wind, right? That's the equivalent of, and so here's somebody listening. That's the equivalent of the source moving. And so the wind was blowing at 12. I'll put a 12 there then for the source and say, look, the source is moving. And that was, as you saw in the homework problems, that one of the ones you had to do with the wind is blowing. But another tough decision here is what sign is this? And so as we work this out, the minus sign when it was moving towards the observer, and the plus sign when it was moving away. And so let's see, the wind of course is blowing this way, but that would be the equivalent of the source moving that way. So there's an important decision I need to make here. Do I do the plus or I do the minus? All right, so I've got the 12, I got the plus. Now let's go to the observer. Now the observer here gets kind of complicated because again, the person on the bike is writing this way at 15. But again, this equation was derived based upon the speed of these objects relative to the sound wave. So in this case, relative to the air. And so the air is moving this way at 12. Now the bike is moving this way at 15. So that's a long way of saying that's really just moving away at 3. The bike rider is only advancing 3 in front of the air. And so again, the tricky part here is being careful about what did we mean by this speed. This is the speed relative to the speed of the air. The speed relative to the speed of the air. So that's how the wind really adds a play to this problem, as well as the temperature. So between the temperature and the wind, we want to be careful with it. And now we're back to the same tough question. Is it plus or is it minus? Well, again, we said the plus if it was moving towards it, and the minus if it was moving away. And so in this case, it's away, where the cyclist is going a little bit faster than the air is coming. So that's why it's a 3, and it's a 3 moving away. And so you should have a minus 3 there, a plus 12 there, a 333 there, a 570 there. When all those are put together, you can then put them in your calculator and get 545. So there's the hard part on that one. And then this one has some motion and maybe more importantly the tension in the wire. It's got two unknowns, but we can also set up two equations. And so the mental picture is something like this. We've got this phone line or cable line. The cable swings up something like this. I suppose there's more, but I'll just make a pulse. And the pulse is going to travel down, hit, and travel back. And the first real clue that I was after was that velocity is the square root of tension over mass density. And the tension is given. The mass is not, the mass is given, but the mass density is not because we don't know the length of the cable. And so that's about as far as we can go with the problem so far. I guess I could simplify the math to something like this, where L then is the length here. Oh, square root. The other side of the equation would be, say, this is velocity, and so I guess this too takes us back to Physics 121. Velocity is the distance it travels and the time it takes. So I'll put a 2L if we're talking about the time to go down and back. And so the problem says it's 325 to go down and back. So I either have to take the down and back distance, or I have to take half the time, and either one would work, but there's my equation. And you can see then in the equation we're given T, we're given M, we're given this T. Don't confuse the two T. This is the T for tension, this is the T for time. Okay, but then the only unknown here is L. So square both sides and you get 4L squared over T squared on this side of the equation. On this side you get tension times L over M, and then one of the L's cancel off. So the complete equation then becomes tension times squared over 4m. And if you put in your numbers, you get the 79.2 meters. So, and again, most of you saw that. Maybe a little mistake, like forgetting the distance here or something like that. But yeah. All right. Make sense? All right. Well, with all that said, maybe I should start by saying, any questions with this week's activities? I'll say it again, or the test. There is no lab this week. There's no MC this week. And Thursday's lecture will be just 1 hour. And I think that'll work well for time. And then we'll see where that gets us and continue on. All right, well, let's go ahead then and begin chapter 20. As I was mentioning, this first part of thermodynamics starts us in a field or an area that I think you've seen before, like chapter 19. I trust you did the homework over the weekend. They ask questions like converting from Celsius to Fahrenheit or to Kelvin, how big things get, okay? And this part of the lesson, if you will, this chapter 20, as you will soon see, is a continuation where we left off. Because we talked about things getting bigger. We talked about their molecular motion moving around. We talked about their pressure coming from the movement of the molecules. But you know what we really haven't talked about yet? Which is what this chapter is about. How much energy does it have? I mean, we talked about warming something up by, say, 3 degrees. And when we said we warm it up 3 degrees, we could calculate how much bigger it gets. But how much energy would that take? And that's what this chapter is in a nutshell. This chapter is titled The First Law of Thermodynamics. This is to introduce you to the idea of energy, or I guess I should say the first law of thermodynamics, because you're already familiar with energy. In fact, here's what's kind of nice about this chapter. Not to say the stuff's going to be that easy, or to say stuff we haven't seen before, but you already know the first law of thermodynamics. You may not have called it the first law of thermodynamics, but I will start off here by saying here is the first law of thermodynamics. The first law of thermodynamics is really the same as the law of conservation of energy. So I'll start there. What did we learn in, I guess this would be Physics 121 again. Chapter 8, what did the conservation of energy say? All right, so you cannot create or destroy energy, right? In other words, the energy before equals energy after, right? Now, the only thing you need to remember, though, is you need to include all the energies. So we're not saying like the kinetic energy before equals kinetic energy after, like that problem we just talked about, right? We're not saying the kinetic energy equals the potential energy. What we're saying is all the energy before equals all the energy after. Here's why I say that. Here is a diagram that I think well describes this chapter. It's a little abstract, but I'm hoping before today's over, and certainly before this lecture is over, and then certainly before this whole unit is over, the abstractness kind of goes away, and you see what I'm talking about. I could have a system. Now, this could be as simple as this. Here is my system. I will take a system. This happens to be some gas. I can close it up. This gas is in the container, although so that I can kind of affect its temperature, I have the gas partly stored in here and partly stored in there. But let's call this my system. And so all the gas in there is my system. Or perhaps I will just grab a simple weight. Here, this is my system. All right, so it's a kind of an abstract word here, my system. But here's the idea of energy. What could I do with my system? Well, in terms of energy, I could add energy to my system, right? I mean, a simple example of that is I could heat it up. But is heat the only form of energy? No, right? There are certainly other forms of energy. Or I could take energy away from it. So maybe I could put this little diagram here. I could say, here's energy coming out of the system. So it kind of makes sense. We will call this the E, right? What's the E of the system? And so to keep track of our energy, we will say, look, if the energy goes into the system, we will say that's greater than 0. Okay? And so as we are doing our bookkeeping, if you will, we are going to do our conservation of energy. We're going to say we can put energy into the system. So we will do that in terms of the system. Now the reason that's important is because if the energy is going into the system, where did it come from? Okay, from the environment, from the surroundings. And so you'll hear those words. So we got to be careful. Are we talking about the energy going into the system? Can we call that a positive? Because that means it's coming from the environment. So the environment loses energy as the system gains. That kind of make sense? Now what about the other side of this? What if the energy comes out of the system? Yeah, we'll label that as less than 0. All right, and so to keep track of this, we'll say, look, if energy comes out, that's a negative number. If energy goes in, that's a positive number. That's conservation of energy. We can put a bunch of energies in, we can take a bunch of energies out. If the whole net effect is positive, that means the system has more energy now than it started with, and it came from the environment. On the other hand, we could take more energy out of the system than we put in, which would mean the E would be a negative number. Fair enough? And if it's a negative number, then that means the energy came from somewhere, or went to somewhere. It came out of the system, and so it is in the environment. I mean, a very crude and simple example of this would be, what if I were to take this and put it under a flame? I won't turn on the flame quite yet, but soon we will. And what am I saying? Well, I'm energy into my system. I'm taking it from the environment. In this case, I'm burning natural gas. The environment has less chemical energy. The system now has more heat energy. In fact, I will kind of label this with a little arrowhead here and put a Q. And in this case, the Q would be represented with a number greater than 0. I am putting energy into the system. Right? Now, after a while, I may stop heating it and take it off the flame and put it over there. Fair enough? All right. Of course, as it sits over there, what's going to happen? It's going to cool down. It's going to be losing energy. So maybe I will represent that with a Q on this side, with an arrowhead pointing out, and a Q less than 0. Right? Saying, look, the energy is coming out of the system. And this little picture is probably the most of thermodynamics you've dealt with. We did this in 102. You've probably done this with chemistry. You heat it up. You have things called specific heats, latent heats. Those things we're going to talk about in just a second. You add thermal energy to it. But where the world gets a little more interesting is watching me draw. No, I mean, what gets more interesting is we remember that there are many types of energy, not just heat energy. And so when I say I add energy to my system, I'll put a W here, meaning I can add energy by work. Well, this is going to take us back to Physics 121 again. What was our definition of work? Force multiplied by that distance, right? Or in this case, it's an integral. So we'll do the math here in just a second. But if we are doing work on the system, again, we're going to label that as positive. Yeah, we'll put a W for work, and we'll say it's positive. You do work on the system. But on the other hand, if the system does work, I don't know why I switched the order here. Actually, I guess I kind of do. I don't really like the fact that I switched the order. But I did. So I don't really mean anything about one being, more important than the other. But I do want you to see that the energy can come out of a system too by doing work. And again, hopefully everything I'm saying here is not a surprise. It's really just making you think about what is hopefully the obvious. It is the first law of thermodynamics, conservation of energy. The energy going into a system adds up to the energy gained by that system. So here is the first law of thermodynamics. E, the energy gained by the system, would be what? Well, I guess it would be the net of the Q's, right? It would be take your Q, and I'll call it net. Meaning, how much heat did you put in? Subtract out how much you came out of the system. The difference between that could be positive, could be negative. If it's positive, then there is a net gain of heat into the system. If it's a negative, there's a net loss. But either way, some of the part of the energy that goes into the system is the Q's. But there's other ways to add energy, which I really want to show you here. That is the W's. Then so I would say W, the net work. So we could add energy by work, and we could take some out. But if one's bigger than the other, then we're going to have positive and negative numbers. The total change of energy of the system is the sum of the two. Your author will write it this way. This is how you will see it in your book. A little bit of energy change. Calculus, gotta love it. DE, right? A little bit of change of energy of our system is equal to a combination of a little bit of change in heat. And so remember, that's the plus and minus. That is the combination of the two. Plus a little bit of work. And so there's the beginning part of the chapter. What is the first law of thermodynamics? And the rest of the chapter is what is the consequence of conservation of energy? What could we do with it? Why do we care about it? And particularly work, yeah?
So why do we make a difference between work and
well, mostly because how we add the energy. I'm glad you asked that because I want to show you a quick demo here. This part, I think, is obvious. And I don't even know if it's worth taking the time to actually show adding energy by heat. There's a flame. And if I were to put something on this flame, there, I'm adding energy to it. I better be careful. That's lead. That'll melt. All right. But there I'm adding energy. That, I think you're mostly familiar with. Not that surprising. But how else could I add energy? It's work. And here's what's interesting. If I add it as work, does the energy have to stay as work? If I have kinetic energy, does it have to stay as kinetic energy, or can it become potential energy or heat energy? Yes. So, we have a very fun experiment somewhere. Aha! There it is. That does a good job Don already took it out of the basket. Okay, so here's the basket. But here helps, I think, our understanding is look at this little contraption. This will be my system. My system will be the air inside this cylinder, right? Now, to put energy into this, I claim there are two ways. I claim there are two ways to warm up this gas inside. One is the obvious. Here's the system. I can heat it up. I can put it on a flame. I can add thermal energy to it and the molecules will go faster. But how else can I get them to go faster? How else can I give them energy?
You can compress the gas and then recompress it.
I can do work on them. And so I'm going to put this piston in here. And I am going to shove this piston down, and in the process I am pushing. I am doing work on the system. And I am adding energy to the system. And what will happen is I do the work, or that energy doesn't stay as kinetic, but it becomes heat, and the gas gets hot. In fact, if it gets hot enough, you can light this piece of paper on fire. And so I have a small piece of paper that I like to keep in a dry container because we get, today's pretty dry, but in general, you never know what the weather is going to be. But what do you think might happen then if I take a piece of paper, put it at the bottom, put in my piston, and do work. Hit it. And I want you to see I can change this energy into this energy. And what's going to happen is I am going to do work. That work is going to change into heat energy. Then my container is going to get really hot. And as it sits here for the next 10 minutes, that heat energy is going to come out to the environment. But of course, in the meantime, to show you and to prove to you it's hot, hopefully the paper will catch on fire. And might be a little nicer to see in the dark. But here, I don't want to cover it, but I don't want to, I got to hold it real good. Can you see that? Yeah? Okay. And it can turn to heat really quick. And then, of course, now it's hot. So I will just leave this here. And what has now happened is conservation of energy. I put work into the system that was converted now into heat, and now it's heating the environment. Now that's not nearly as exciting as what we're really after. Could I take heat and convert it into work? And I'll show it again. This is what we're after. If I take a small system and I want to lift that load, I can put it in hot water. And I am taking the energy from hot water and converting it into work. And that's really where we're headed here. I want to burn the gasoline and make the car move. It's not so much I want the car to move, come to a stop, and heat up the world. Although that happens, that's not often the intent here. But I use these little corny pictures here. Do you see the picture now? Do you see what this diagram is supposed to represent? It's pretty abstract, but it represents our conservation of energy. It well represents our Newton's first law of motion. First law of thermodynamics, not first law of motion. Yeah.
So does that mean that putting the ball in the water without the weight would have less effect on the water than with the weight?
Yes. Because again, because I think what you're saying here, and you're answering it with the first law of thermodynamics, when the weight sits on top, that's more work than if the weight wasn't, right? And so where did it get its energy? It got it from cooling the water, right? So when I put weights and lift it, I cool the water more than if I didn't put weights. And my first warning, it'll come many times this chapter and next. That means calculating how much heat and work is highly dependent on what's going on. I wish I could just give you one formula and this is the answer. But as you're going to see, what makes this section hard is calculating how much that water cools down is based upon how much work was done. And how much work was done is based on the conditions of how the work was done. So every problem is unique in its own self. So we can talk about these grand general properties. But as we go to apply them, we got to be really careful. Every situation is uniquely different. So good, I'm glad you noticed that right away. Well, maybe I spent too much time here at the beginning because I do want to review some things that I know you saw already in Physics 102, but I wanted to set this picture. This is the big picture. This is the first law of thermodynamics, to study heat energy and work energy. The heat energy you've been doing many times. Watch. I bet if I were to come over here and put this on the board and say something like, okay, let's start off with a simple system and just heat it. Forget the work for just a moment. And so I'll put this one away for a little bit. In fact, what I will do, so I can use it later on, is open it up and let some fresh oxygen get in here so we can do it again later. All right, so I'll let that, make sure there's oxygen inside when we're ready to go. But what I wanted to jump back to is this lead block. And in fact, maybe I'll take 2 lead blocks. I deliberately brought 2 out here today to say, all right, let's talk about the energy of warming up these 2 lead blocks. And again, let's just forget about this section for a moment. That's coming. But let's just start right there. Do you think it would take the same amount of energy to warm those up? No, why not? So I would expect, and I'm hoping you do or too, that big block, even though it's made out of lead, to take more energy to warm it up 1 degree. Why?
Because the temperature distributes equally in the
Yeah.
system.
Okay, so there's just more of it, right? Right? I got a lot more material here than there. And so what your author does first is he says, let's talk about what we call the heat capacity. And the heat capacity is just saying how much really heat can this thing store, or how much energy is needed in order to warm it up 1 degree. And so when we take our system and we just simply put a flame underneath it, what we could say is we are adding energy. We are adding heat. And the heat capacity then would be this Q. Have I used Q? I have been using Q, right? But maybe I did that without mention. We like to use the symbol Q for heat. Did we do that in 121? Yes. Yeah? Okay. All right. So Q is the symbol for heat. But if I took the total heat that I had to add to that and I divided it by the temperature change, that's what we would call the heat capacity. How much energy does it take to warm up that object 1 degree? Now, what I'm getting at in terms of the physics here is that's not often very useful to understanding the physics. Now, it's very interesting to talk about the result. For example, would it take more energy to warm up a cup of water or an ocean of water? Wouldn't it take more energy to warm up the ocean? So I would say the ocean has a lot of heat capacity. Why? There's a lot of water out there, right? And it's going to then take a lot of energy. In fact, that's why we love our Santa Barbara weather here, is because it does have a large heat capacity. What happens in the summer? When the sun comes up and it's shining and the air tries to warm up, notice I say tries to warm up, what happens? Then that hot air tries to warm up the ocean. It's going to take a lot of energy to warm up the ocean, even 1 degree. And as you know, it can be summer, but our ocean is still kind of cold. But the added benefit is, what does that say about the ocean? It stays cool, right? It's very difficult to keep the air around Santa Barbara because the ocean has such a large heat capacity. And better still is winter. What happens in winter? Ocean keeps us warm. I mean, good luck letting the air get cold. I mean, this morning I looked at my thermometer, it was 42. Ooh, it was cold. But it was difficult for the air to get that cold, because what do you think was happening all night long to our ocean, which is at 55 degrees? Yeah, that ocean's been all night keeping the air warm for me. And so inland areas, they were getting cold. Our temperature dipped below 55, and all of a sudden the ocean's just sitting there all night going, oh, no, I'll give you some of my heat. Giving you some of my heat. Does its temperature change? A little bit, but not much, because of the large heat capacity. Now, I shouldn't spend too much time here, because we don't really spend too much time with the heat capacity unless we are interested in, like, say, the whole size of the environment or the whole size of the engine and saying how much energy does it take to warm up the whole engine. But from a physics point of view, it's very clear that it takes more energy to warm up this than this because there's more mass. So what do you think the next step should probably be? Yeah, what is the heat capacity for every gram? That's a much, I don't know if I want to say honest, but a better physics answer of how do I compare one material to another. Not just because the material, I have more of the material, but just how much do I have. So you probably know this as the specific heat. And so the specific heat is what you learned in your 102, and I think you also did in your chemistry, and you probably saw also in some high school classes. But this then is called the specific heat. it is more of a description of the material itself than it is the size or the mass of the material. And so the symbol we are going to use is C, meaning the energy needed to add to a system to warm it up would be this. And so maybe I'll call this equation 1. Well, I can get in trouble if I start numbering them because I won't be able to keep track of them. But this is our simplest one, and the one I think you've already seen before. This is this part here that when I had this lead block on here and I was going to either say, I'm going to warm it up 10 degrees, how much energy is that? Well, the energy needed to warm it up 10 degrees depends on these 3 factors. One is how much you're going to warm it up. The other one is the specific heat. This is the part that's related to the material. How much energy does it take to warm up that material? And then, of course, the other one is how much material do you have? So if I change my discussion and say, all right, and this probably isn't a fair discussion either because I don't have an equal amount of aluminum. But let's just say for the conversation, I have an equal volume, which is unfortunate, an equal mass. But let's say I had an equal mass here. I would again ask, does it take the same amount of energy to warm these up? No, because they are different materials. And the bonding between them is different. And so it's going to take, in this case, more energy to warm up the aluminum if you look at the specific heat of aluminum. And so I want to point that out. Table 1 of this chapter shows what is the specific heat of a bunch of different materials. And so that's how we classify our materials in how much energy does it take to warm it up. And what you'll see is aluminum is a much bigger number than lead. How much bigger? 9 times? Well, I won't bother to try to remember what it is here, but I know it's in that first table. And the point is, it's telling me something about the material. It's telling me a little bit more about the material. And that would be a fun conversation in itself, but we better not spend too much about the molecular bonds and the material strength of it. But that is telling me how much energy is needed to warm up that material. And it's different for every material. So keep an eye on that. Yeah.
So why would they use aluminum for heat sinks? Wouldn't that be a disadvantage?
No. The real advantage of using aluminum for a heat sink is not so much how much energy does it take to warm it up. Although the fact that it has more energy to warm up than this is a good one because that means it takes a lot of energy to go in. So I think you're thinking of this backwards. You would want a heat sink to have a high specific heat because you would want it to go in to here. But the real advantage of aluminum for a heat sink is that it moves heat. It conducts heat from one side to another. So if I were to put something hot on this side would get hot very quickly for aluminum, but not for lead. So lead does not make a good heat sink because it doesn't move the heat from one side to another. And so that's conduction. And I will get to it, but probably not today. But it's in this chapter. Yeah.
What are the units for M and...
Oh, okay. So the units here for specific heat would be what? This is heat. So what units are we going to use for heat? Good, I hear both. We could use joules, but we could also use calories. So you will see in your table that they have 2 sides to the chart. One side of the chart says how many calories. The other side says how many joules per gram for each degree Celsius. I said I wouldn't call up the table, but I lied. Let's take a moment to look at chapter 20, table 1 here. Table 2, table 1. But if I look at table 1, you'll see exactly what you're asking. What are the specific heats of these different materials? What are the materials? So across here, aluminum is 900 joules per kilogram. Oh, I put grams up there, so they have it in, so they have it in grams for the calories, but they have it in kilograms for the joules here. But any unit that has energy in the numerator and mass and temperature in the denominator. And by the way, I should point out, even though they have Celsius here, notice that could be change in Kelvin also, because a change in Kelvin and a change in Celsius are the same numbers. But as I was mentioning here, the aluminum is at 900, the lead is way down here at 128. Okay, so what is that? 6-7 times more energy to warm up the same mass with that one, that 1 degree here. And so taking a lot more energy to warm up aluminum. That's why aluminum blocks are a lot harder to warm up in a car than they don't have steel, but I'll put iron on here. It just takes a little longer to warm up, which just can be a negative thing because it takes out much longer before your car is running at its peak performance, because it's designed to operate when things have their thermal expansion. But that's okay. Once it warms up, we got it. So maybe that's worth it, and it certainly is worth it in terms of fuel economy, because now we're pushing something a lot less in weight than we are when we had it made out of steel.
It specifies the different heat, temperature, and pressures. Is there a big difference between?
They do change. I mean, this is something that depends on how the bonds are, and the bonds depend upon what temperature they are and how they're interacting. So it does change slightly. So for an introductory physics thermodynamics class, we say it's the same over the whole temperature range. Yeah. So that's going to be our approach. You may have slight modifications to that the next time you take thermodynamics, which would be when you transfer. And I think this is always the one where students come back and tell me that you didn't tell me everybody's got to take thermodynamics. So pretty much all of you, regardless of what field you go into, unlike say optics or unlike our mechanical waves, or unlike our E&M, I think all of you are going to have to take an upper divisional thermodynamics. I'd be surprised if that wasn't the case.
Over large temperature variations, does the specific heat of any element or molecule change?
Yeah. So it will change.
Linear, right? I did the meeting last night.
Well, roughly. Yeah, very roughly. But again, for us, let's just do this. Let's just say this is the specific heat of aluminum. And if you're warming aluminum from 50 to 55, we'll treat that the same as if we're warming it from 20 to 25. Same amount of energy. It's 5 degrees. That's the change. Okay? And as long as I called it up, I should point out water. Look at water. Water has an extremely high specific heat. So you put the fact that the ocean is very big, together with the fact that the specific heat of water is very big, a 1 degree temperature in an ocean is an enormous amount of energy. And so a change of an increase or a change of a decrease of 1 degree is talking about a lot of energy. And that's very lucky for us. That means our world is a little stable because of all that water keeping us. So, and hopefully we as humans won't destroy that real soon. But we've been very fortunate over the last 20,000 years that ocean has really kept us at a constant temperature and let us humans survive. Yeah.
How come ice and steam are roughly the same number, but liquid water is?
First of all, let me point out they're different than the liquid.
Yeah, because they're different temperatures.
It's not just different temperatures. They're in a different state. The bonding between them. And so, right. So I want to emphasize the fact that the materials all have a different number is a testimony to how the energy interacts with the bonds between them. Okay? So that's why things like aluminum have had such a high specific heat, or things like water have a high specific heat, because when you add energy to them, what you do is add energy to their bonds, you don't add energy to their motion, or very little energy to their motion. So you got to add a lot of energy just to make their temperature go up 1 degree, because most of the energy you're adding is going into their bonds, not into their motion. And so all of these numbers are different because of the way the bonds in the material is. And so this is something that you would find very interesting, because it goes right to the heart of material science. This tells me something about the bond strength. And so that's why water liquid would be different than water solid, different than water steam. Now, you were asked a bigger question that I think is just coincidental, or if there's more to it, I don't know, that steam and water happen to have roughly the same numbers.
Yeah.
Yeah. No, steam and ice, sorry. Yeah, steam and ice have roughly the same numbers. No. Well, anyways, I better keep going here, because that is one way of talking about the specific heat, or talking about energy. That's equation number 1. But let me change it. As you could probably see here, I would say, talking about the specific heat, that is, how much energy does it take to warm up 1 gram of aluminum and 1 gram of lead, is also a little misleading. Because what do you notice dramatically different between 1 gram of lead and 1 gram of aluminum? And I'll pass these around if you want to fill them. But the weight of these are very different. And so when you hold 2 objects that have the same size, they have a different weight. So when you say how much energy per weight, that can be misleading. So let's take this one step further. Whereas you've probably done specific heat in your other classes, you may not have done molar specific heat. What do you think molar specific heat would be? Heat per mole. How much energy does it take to warm up 1 mole? Whether that be 1 mole of aluminum, or whether that be 1 mole of nitrogen, or whether that be 1 mole of helium, doesn't matter. What matters is we're comparing equal number of atoms and equal number of bonds. And that can tell us a lot more information and be much more useful for us, as you will see here, about how much energy. So usually when we deal with solids and liquids, we like to deal with the specific heat, because we can say how many grams do we have. But when we start dealing with gases, we like to deal with the molar specific heat. How much do you have per mole? And so I'll put a Q here. What was the symbol we used for number of moles? Little n, right? Oh, thank you. And delta T. Almost forgot that one. Yes. Yes. So again, to make a fair comparison, I want to make sure I'm warming it up 1 degree and an equal number of molecules. And so that's called the molar specific heat. Now, the symbol we like to use will either have a subscript P or a subscript V. More on that in just a second. I'm just going to leave that alone here, because we'll even divide that into categories. But I think you guys had already seen it back here. What if I were to take this apparatus again, maybe right about here, and I will clamp it here. The clamp means that this piston cannot go up and down. I'll put the weights on here just for fun. Actually, maybe I should let it all the way be down first. Okay, then I'll clamp it. And if I go to add energy to this, there would take a certain amount of energy to warm up this gas 1 degree. Fair enough? But on the other hand, what if I didn't have a constant volume, but this was loose? And so as I'm warming it up, not only does the gas warm, but as the gas expands, it does work. And what you noticed already is, wouldn't it take more energy to warm it up during the process that this went up? During the process of constant pressure would take more energy? Because not really are you only adding energy to make the molecules go faster, but where else is that energy going? Out of the system as work. So I'm claiming that the molar specific heat is really coming in two flavors. The first one is, do you warm it up at a constant volume? Or do you warm it up with a constant pressure? And this is, again, that warning. The second time I'll say it today. How much heat is given to our gas depends on how you heat it up. Do you warm it up with a volume that is held constant, or do you warm it up with a pressure that is held constant? Or, and I'm only showing you two of the beginning possibilities, the easiest two. But you're beginning to see then there would be a different number here. And I'm hopefully you're also seeing which one would be bigger. Which one would take more energy? Constant pressure. Why? Right, back to this picture again here. I'm adding energy. And as I add energy, if the gas doesn't expand, if the gas doesn't lose any energy by doing work, then it might only take a small amount of energy to warm this up 1 degree. But if you start adding energy to it, and while you're adding energy, some comes out, you're going to end up having to add more energy to it to get it up at 1 degree. It's like adding water to a leaking bucket. If you have a 5-gallon bucket that doesn't leak, you put 5 gallons in, it's full. But if you have a leaking bucket and you start putting water in, by the time you fill up that bucket, you might have had to add up 6 gallons of water because 1 gallon leaked out the bottom before you could get it filled, right? And that's exactly what makes this section and this whole unit a little more complicated, is equation number 2. How do I calculate the energy? Well, depends what its mass is, depends what its temperature is, or depends on how many moles I have. And that's that little subtlety there. All right, well, I better keep going and keep talking about this energy, because again, this chapter is all about the energies. How can I add the energies? Where could they go? Well, this is adding energy so its temperature changes. But what would happen if I really did warm something up, like ice, for a long time? I mean, if I were to start with a bunch of ice, and I would ask myself, okay, here's some ice, and actually let me just put a little water in the bottom so that I don't crack the bottom of my beaker and it gets too hot. But I think you know what might happen here if I were to just start adding energy. And again, simple case here. Add Q to my system. Now, this ice happened to become out of the freezer at negative 30 degrees Celsius. All right. So if I were to make, say, a plot here and say, trying to decide if I should erase, I'll go ahead and erase it. But this picture, like I said, really explains this whole chapter with our first law of thermodynamics. We're just going to keep adding energy to it. Oh, that's your paper. I thought that I thought my water was doing something funny. It was going to crack. I heard something tearing there. All right. But if I were to make a plot here of the temperature versus the energy that I add, okay, knowing that I got this ice out of the freezer, it was at negative 30 degrees Celsius. And the truth is, it's probably has warmed up from 30 degrees because it's been sitting in this room for a while. But assuming I got it instantly out of our freezer at negative 30, and I placed it under here, I would add energy. And as what we were talking about with this equation, the specific heat of ice here, or at least in this area, is this 2090. If I gave you the mass, couldn't you calculate how much energy it takes? Let's just say I had 1 gram. Now, for demonstration reasons, I have a lot more than 1 gram. But I did the numbers with 1 gram, and I said, all right, let's say you have 1 gram. How much energy would you have to put in order for it to get to 0 degrees? And fortunately, I don't even have to do an integral. It's right here. It's simple algebra, right? How much energy? Mass is 1 gram. Specific heat, change in temperature. You put those numbers in, and you get 62.7 joules of energy. That was kilogram, right?
Right, that's correct.
Yeah. Hope I did that right. All right. Maybe I should check. Did I? I think I did these numbers with 1 gram. I'm sure I did. Yeah. And so that's what was happening at first. But here's what I want you to see. Here's the next piece of this energy puzzle that this whole chapter is out. What will start to happen at 0 degrees? Right, and so the mental picture I want you to have is back when it was a solid, if each little round ball represents H2O, they're hooked together. And when they were less than 0 degrees, these were shaking, and as I warmed them, where did that energy go? Well, it made them shake more, right? And it was also going into the bonds. But at some magical temperature, as these shake and shake, what happens at some point when they shake too much? They stop looking like this and start looking like this. And so what happened at that magical temperature is all the energy at that point starts going into breaking the bonds. None of the energy makes the molecules move faster. So while I'm adding energy at this point, can never seem to keep track of a marker. All right. Is from here on over to here, adding energy breaks bonds, and only breaks bonds. It doesn't make them go faster. And when I'm trying to say that, what would happen to its temperature then? Yeah, its temperature would never change. And so during this part of the process, you would have a combination of both ice and water. And in this case, we would get a total energy of 396.6 7 joules of energy. And so what I'm trying to say here is there is going to take a lot of energy to break the bonds. It could be misleading because did the temperature ever go up? No. But did it take energy to break those bonds? Yes. And so to convert a solid into a liquid does take energy, but its temperature doesn't go up. This is called the latent heat of fusion. And the idea of latent is Latin for hidden because the early scientists were confused. They didn't understand what was going on. They just knew they kept adding energy and the temperature didn't go up. And what they didn't understand, which hopefully you now understand, is where's that energy going? Right there, breaking the bonds apart here. The reason that's important then is what would happen if you went from the liquid to the solid? Yeah, you got to give that energy back out. So breaking these bonds takes a lot of energy. The symbol we like to use is L sub F. That is the amount of energy per gram. How much energy does it take to break the bonds of 1 gram? Question?
So we put energy in to break the bonds.
Yeah.
But to create bonds, we take energy out.
Yes. So if we wanted to make ice, what do? We put it in the freezer.
Right. I think it's weird that you create something by taking away energy. You're creating bonds.
Well, you might.
They want to be in that structure.
Well, how do you stop a car? You take energy from it, right? You take energy from it, and that makes a slow car. You put energy in, and you get a fast car. Same thing with the molecules. If I want the molecules to go fast, I put energy in. I want them to go slow, I take energy out. Okay. Yeah.
I thought that the bonds for ice form back once it gets to a certain temperature, thermal temperature, but you end up with supercooling unless you shake it a little bit.
Well, okay. Again.
Purely
Okay, again, there's super subtleties here that go beyond an introductory level. But water can be very interesting because, if, for those of you who aren't familiar, water doesn't really like to start forming the bonds on its own. Yeah. So if you had actually pure water, unfortunately we never do have pure water. We always get it out of the tap, and we always have a bunch of minerals and sodium and magnesium in there, calcium. But those bonds will form then around those calciums, and so most of the time this will happen. But it's true that you can get what they call a supercooling. What you said. Yeah. Anyways, I'll keep going with this because hopefully you see here in the picture, I've changed to this diagram then to table number 2. And again, here's our substance. See, I'm giving it to you for water. Here's water, the melting point at 0 degrees. How much energy does it take? This is how much energy it would take to melt 1 kilogram. They have it listed in kilograms. And so, of course, if we were melting a bunch of ice, like we tend to be doing right now in the polar regions of our globe, that is a lot of energy. It takes a lot of energy to melt all that ice. And again, we're fortunate to have all that ice. All the heat we keep putting in doesn't warm up the Earth. It breaks the bonds of the ice. When all the ice is gone, that'll be different, I suppose. The Earth will warm up pretty quickly by then. But that's where our energy is going.
Should we try to remember any of these numbers?
No, these would be given on, yeah, you don't need to commit them to memory. The water you probably will because you'll use it so much on the homework. but certainly not any of the others. But again, notice it's all these other materials. All these other materials have the same basic idea. When you go from the solid to the liquid, you got to break the bonds, and it takes a certain amount of energy for that to take place. That's my point, and that's the point of this whole chapter, to talk about the energy, the type of energy we have to deal with. And so this is breaking the bonds. Now, I talked so much that you already saw the next step. The next step is that once all of the ice is gone, that is, once all the bonds are broken, what begins to happen now? Yeah, now I guess once all the bonds are broken, we're back to this stage where we start to change the temperature and the molecules start to go faster. So I would go from water at 0 degrees and it would warm up until it got to 100 degrees. How much energy would that take? Well, again, I can get this equation. So, if I was calculating how much energy, I would use this equation when it was a solid. I would use this equation as it was changing states. Now I'm back to this equation again as I'm warming it up from 0 to 100. And once I get to 100, what happens? It takes a lot of energies to break the bonds completely. You might say, where's my liquid, that once we broke them into here, once we were at this step here, we started to warm them and they started shaking more and more and more and more. And then what happens when they shake too much? Well, they go from looking like this, a liquid, to looking like that, a gas, where there's no hooking between them. And they would just float on out in the atmosphere. And that's what you're seeing here now. This has been shaking so much that they are now breaking and floating out into the atmosphere. But again, that would take a certain amount of heat. There is what we would call a latent heat. There is an energy needed to break those bonds. When you're at 100 degrees, like right now, as I am pumping and pumping in more and more energy, is the water getting any warmer? No. What temperature is it? 100. It's 100 degrees. And as I add more energy, the molecules don't go any faster. The temperature doesn't go up. Where do they go? Breaking the bonds, and in this case float away, and it's out of the system, as you said. And this is a lot of energy. We call this the latent heat of vaporization. How much energy does it take? We call it LV, Q over M. How much energy does it take to break those bonds? Again, that's the other part of the chart. An enormous number when it comes to water. And so boiling water is going to take a long time to boil away, as you can see. Question?
So no molecules from the water will vaporonize until we get to 100 degrees?
Well, there's some on the surface. Let me answer it twice. The simple answer, I'll say no. I'll say none of the water molecules break apart. They just go faster, 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 and faster. Truth is, remember, these are random collisions. So there's always going to be some molecule near the top that as it's bouncing around gets hit maybe by two at the same time. And that one molecule is going the equivalent speed of greater than 100 degrees Celsius. And then hence that one, what we would call, evaporates off the top. And so you will see an evaporation off the top. But statistically, none of them leave, because if one is leaving, the other one isn't leaving. But only the fast ones would be leaving off the top. And they would be breaking the bond, so they would take a lot of energy with them. In fact, I'll show you that in just a second here. But I want to make sure I got this clear here then. Here is calculation number 3, if you will, that I can figure out how much energy is going into or out of my system based upon how much mass do I have and what is this latent heat of vaporization. So again, scanning across for water, we know we'll need to get to 100 degrees before this happens, but when it gets to this boiling point at 100 degrees, it will take this much energy to completely break the bonds. And that's a huge number. And so as you can see, I've had boiling water here for quite a long time. And it's going to take a long time before all of that will boil away. A lot of energy. And of course, the reverse is very true. In fact, thinking about this lecture this morning, I was kind of tired this morning and I had a hot shower. And it was cold when I got up in the morning. But by the time I got out of the shower, it was cozy warm in the bathroom. Why? And the mirror was covered with steam. Or I should say water droplets. Why? How did my bathroom warm up? This water moisture that is floating around in the bathroom and then condenses. What does it do? Releases all that energy. So remember, conservation of energy. If it takes this much energy to turn it into a vapor, it takes a lot of energy to give back when it condenses. And in that case, that's what warmed up my room. If this was a big plume of moisture over the Atlantic and it all turned to clouds and started to rain, what would happen to that energy? It would turn into wind, and I'd call it a big storm, maybe a hurricane if it was big enough, right? And so there's the strength, there's the energy source of all of our storms. Where do they get all that energy? The energy comes from right here as the moisture is condensing back. Pardon me? Well, the wind blows around and eventually ends up as heat energy. Or gives some of its energy to the waves, and the waves come rolling into our beaches. So then it's wave energy until it turns to heat energy when they end up on our beach. Yeah. Or if this is a hurricane that hits land, it blows houses around, and you've got kinetic energy of pieces floating around. They usually hit something and turn into heat energy. So eventually it all ends up with heat energy here, but that's a big number. In fact, to illustrate it, I thought I would bring a couple things out here to kind of show you. Here I have a bucket of alcohol. I picked the alcohol because it evaporates so much quicker than water. But to illustrate it, if I were to put my thermometer in the alcohol, which, as you saw, has been sitting out in this room for the last hour and a half at least, and then a couple hours before that when I got ready, it's 20.4 degrees Celsius. That's the temperature. By the temperature of this room, it's the temperature of this bucket of alcohol. But if I were to then pull this out and just hold it out in the room, what's the temperature now? Yeah, for those of you who are close, what does it say? 13 degrees? It dropped from 20 to 13. How and why? Yeah, because as the molecules evaporated, as you were asking about, they are breaking the bond. They are taking with them the energy. The ones left behind on the temperature scale here have a very low temperature now. And so we often refer to this as an evaporational cooling. It's a first law of thermodynamics. It is how much energy is needed to break the bonds as these things come off of here. And so once it's all gone, it starts to warm up to the room temperature. And so, quick demonstration again, quickly dropped. And it wasn't the temperature of the liquid that made it drop. It was the evaporation. If you've ever spilled some rubbing alcohol on your hands, your arms, you will feel that coldness right away. That is evaporating off. And as it evaporates off, we could calculate. Where's alcohol? Oh. And so we could calculate how much that is, although I have methanol alcohol up here, not ethanol alcohol, but I'm sure it's probably close. Yeah.
The temperature on the reed decreased specifically because the atoms or the thermal energy of the metal bumps against the alcohol, and the alcohol, instead of bumping back and keeping an average heat, just flies off into out of the system into the atmosphere?
Exactly.
Okay.
Exactly. And so that's where the energy goes. Do you still have a question? No. Yeah.
No, it's just like I was thinking like when you discuss low pressure and how it evaporates easier in low pressure, but
Oh, well, okay. I'm glad you say that because I'm going to do that here. Maybe I should have left this on, but when you were watching this thing boil, of course, I put it here so that you could see it boil. I was mostly interested in making you understand this graph and the energy, and then, of course, how you're going to calculate the energies. And so we could calculate the energies this way. We could calculate the energies this way. We could calculate the energies this way, right? Depends what we have and what's going on. Are we changing temperature? Are we changing phase? If we're changing phase, we calculate it this way. If we're changing temperature, if it's this way. If we go from a solid to a liquid to a gas, we've got to do this twice because it changes two phase, and we got to do this 3 times. Once for the solid, once for the liquid, and once for the gas. But this right here is what most people think of when they think of boiling water. I mean, look carefully at it. Where are the bubbles being formed and why? At the bottom, right? I'm putting heat at the bottom. The molecules at the bottom get very hot, and they get hot enough that they break the bonds and they turn into a gas, and of course then they rise. And of course, as we learned in the last chapter, as they rise their pressure will change, although there's not too much change of a pressure in that short of a distance, but their size will change. And so you're used to seeing boiling water starting at the bottom and coming up. You're probably not used to thinking of boiling as a cooling process. But isn't that what I was trying to show here with the evaporation? When these molecules break off, isn't it keeping this thing cool? Isn't that where the energy is going? You could say the whole reason this does not warm up more than 100 degrees, even though you're adding energy, is because the molecules that boil off are cooling it. So how do humans cool themselves? Sweat, right? It's the perspiration that keeps us cool. And so just like this alcohol evaporates off, if our body puts moisture on the surface and then those molecules come off, that is our cooling process. And fortunately for us, it's an enormous amount of energy. Just evaporating 1 gram of water is 540 calories worth of energy. That's a lot of energy for 1 gram. And it can keep our body very cool. And so if we are playing a game of volleyball out on the beach or running a marathon in the desert of Death Valley like my crazy friend likes to do, you know, he literally drinks 15 gallons of water during the race because it just evaporates. And his body doesn't overheat, and he's not taken out of the medical facilities like other people are, because he's kept his body cool by evaporation. So watch this. This one is a cup of water inside a vacuum. Behind here is a giant vacuum pump. I'll spin it around in case you want to see it. But it is a good size vacuum pump, and it will take the air out of this chamber. Now, reason for that, which not really covered here, but when we say water boils at 100 degrees Celsius, what do we really mean? At 1 atmosphere. In other words, these molecules that are shaking around have to shake up to 100 degrees before they will break free. But what's keeping them in here is not just the bond between each molecules, but also the air pressure that's holding them in. So if you lower the air pressure, what's going to happen to the boiling temperature?
lower.
It's going to go down, exactly. And so the boiling temperature changes with pressure. Now the reason I say that is because I would like to show you boiling water without a flame. If I lower the pressure, the boiling point could get less than 20 degrees Celsius, which is the temperature in here. And I can get that to boil even though I don't have a flame underneath it. But the neat thing is, once it starts to boil, what happens? All the stuff that boils away takes energy. So what about the stuff left behind? It's going to be colder. You don't see it here because you have a flame underneath it. You will see it here because we don't have a flame under it. So starting at a temperature of 21 degrees, turning on the pump, letting the pressure go down, down, down. You will eventually see it starting to boil. You'll see a very different looking boiling. Forgetting the tip of the metal, it looks like it's bubbling near the top, right? Because which molecules turn into a vapor? The ones near the top. Unlike these, the ones near the bottom turned into a vapor because the flame was out the bottom. Here, the ones at the top, or the ones that are disturbed by, in this case, the temperature probe, they do at the bottom of the temperature probe. But I claim that for every gram that evaporates out of here or boils out of here, will take 540 calories. And so what's left behind should be at a lower. Ooh, 20.7. Not that exciting. It takes a long time. But this, as it evaporates out, will get colder and colder and colder. Yeah?
Could it ever get so cold that the water in there eventually starts?
Oh, it could. Not with this pump. The pump's as big as it is, it's not big enough. That handheld one that I often take into class that you've seen is not big enough to make it boil in class. So I got to use this one to make it boil. This one is not big enough to cool it down to freezing. But left long enough with a strong enough pump, it could go into a solid, definitely. Yeah.
So all you're doing to that is you're just getting the pressure to 0.
Yeah, I'm just lowering the pressure as low as my pump will get it. Right, and the point is now the boiling point of that liquid, water, is less than room temperature. So it should be boiling. And then conservation of energy. First law of thermodynamics says if that's boiling, some of the energy is going into the vapor. So the energy left behind is less. And so the temperature should be less. So I'm essentially taking the temperature of the liquid and giving some of it to the boil. So the other stuff left behind is colder. And that's something you can't really see with a higher boiling point. Yeah. Oh, yeah. If I turn it off, what will happen is the vapor will come in here and start building up pressure right away. That pressure will get higher than, or high enough pressure that the temperature of this is, I'm not saying this right, the boiling point of the liquid will be greater than the room temperature and it'll stop boiling. So yeah, to get it to boil, I got to get that vapor out of there. So it'll take a little while. You can see the vapor on the side. But once I get all that vapor out of there, then the boiling temperature, boiling point is lower than the room temperature and it'll start boiling again. But as soon as I turn it off, that's why, as you said, I can't get this to freeze because the vapor comes out of here at such a rate that my pump can't handle it and I don't get it cold enough, fast enough to get it to freeze. But it could happen. All right, well, I'll keep going because I would say at this point I've done the easy stuff. I've done the stuff that is calculating the energy by heat. I'll clear the board here and say, all right, what you've seen so far is this. You have seen in our little diagram where this is my system. You have seen the flow of energy into the system as heat, a Q. You've also seen it coming out. And since I started my drawings with the Q down below, I'll put the Q down there. And so this is energy going in, which I would call greater than 0. This is energy coming out. But I've only done half the problem here. How else can I add energy to my system? Right. And the whole point of showing you this earlier was to say, I can also do work. So let's talk about that for a little bit. How much energy do I add by doing work? Or how much energy comes out by doing work? And so, as you already saw, I can either do work on my gas, I can squish it, and so maybe coming back over to here and kind of resetting this, maybe there. Besides just heating this, I can come over and push on it. That would do work. Of course, you saw the extreme case earlier where I pushed it really hard, really fast, and had a huge change, and so much work, the temperature went high enough that it caught the paper on fire. This would be just a certain amount of work that probably just is turning to heat also, and is slightly warming it up. And that's what I'm getting at here. How do I calculate work? Well, let's go back to physics 121 here. How did we calculate work? What do we say? Yeah, force times distance, right? And so I'll put a W, but let's do a little bit at a time. Because if you think about this gas here that I'm squeezing, whether it was this one or kind of that make-believe one there, or not make-believe, but I actually squeezed it, it just wasn't that warm that anything caught on fire. But this one, where I squeezed it here, I would have to say the work done here is force times the distance I compressed it. Do you remember that? And of course, notice I wrote it in calculus form. Why? Well, let me draw a little picture over here. Let's take this little cylinder here, and so here's all of my gas molecules. If I come along and I push on this gas, let's just say I push a short distance. So from maybe here to here. That would be my dx, right? That is the distance I pushed it. And what I would want to know is how much force. But here's where it gets interesting. Every little distance I push may not have the same force. It'd be great if it did, because then it would just be a constant number F times the whole distance d. But what if it is not a constant force? What do I need to do? How do I get the total work as I go from some initial point to some final point? Yeah, wouldn't that be an integral from some initial to some final of f of dx? Now, the reason I say the force may not be a constant, let's go back to this last chapter 19. We learned that the pressure inside a gas depended on its volume. And it changed as the volume changed.
So there will be more pressure.
So I got to keep that in mind, that it becomes hopefully very clear that if we're talking about the work done by the gas, and so maybe I should say the work done on the gas, I am talking about the force from the gas. And so I am claiming the force from that gas is related to that pressure. And so if I keep in mind that pressure times volume equals nRT, then as I am squeezing this down, the volume is changing. And maybe the temperature too. Kind of depends how I squeezed it. But if only the volume changes and the temperature doesn't, that still tells me the pressure changes. If both of these are changing, well, that just tells me the pressure changes in even a more complicated way. Simply put, I got to do an integral. I can't just say force times distance. This has to be an integral. And the integral depends on how the pressure changes, and how the pressure changes depends on how I squeezed it. So, third time today, warning again, one of the things that can make this chapter hard is we got to think about how are you squeezing the gas. For example, if I came over to here and I were to put this in my container of hot water and let it kind of expand on up and settle in there, okay, so this will be my starting point. If this is my gas now, as I go to push on it, the pressure is building up. And I have to do an integral. And I would say a rapid push on this, I would have hit those molecules so hard that they would have started moving faster and the temperature would go up. But the fact that it's in here means that as the temperature goes up, the heat energy moves out to my reservoir. So the fact that it is sitting in the reservoir, say, I am pushing this, but I am pushing it down at a constant temperature. Whereas if I left it out in the room and maybe wrapped it in an insulating towel so when it does warm up, it can't cool down, then I would say I'm compressing it a little bit different. I'm compressing it and letting the temperature change. And so how I compress it depends on how the situation is set up. And how the situation is set up depends how the pressure is related to the force, and then the force and how I do the integral. And so I got to stop and think about all the different scenarios. And we'll run out of time for today, but that's what we're going to focus on. What if you compress it with constant pressure? What if you compress it very quickly? What if you compress it at constant temperature? What if? Yeah.
Didn't you just say mgh is how much energy that you lost, and then calculating how much energy is you solve for energy?
No, because we don't know. Well, in this case, the mgh is if I did that, right?
Yeah.
Okay, that wouldn't be so bad. But what if it's this?
Then you have to calculate how much you're pushing down on it.
Okay. And would it be better to calculate how much my hand pushes on it, or how much the gas pushes back? It depends what we know better, right? Yeah. I mean, if I knew this force, then I would agree. That's kind of simpler approach. And then I'm just using conservation of energy. The energy lost from the outside world equals the energy gained there, right? But I got to be careful. I just know the energy gained. How much goes to heat? How much goes to work? Well, I guess in this case it doesn't have another piston expanding, so none would go to work. So yeah, that would be an easier approach.
In the situation of a gas compressed by a piston, so something like a gasoline or a diesel engine where there's the compression chamber, is there any energy loss to sound, or does the sound convert back into thermal against either the metal or the piston or against the piston? Because there'd be shock waves from the sound, and they would just push against the piston.
Both of those are true. One, they would go back to heat. Two, the energy in sound is so small.
If you
We're
wanted
gonna worry
to
about
calculate the energy from one piston during one combustion,
Yeah.
finding a weight
Yeah.
on top of your piston.
Yeah, and that's eventually where we're headed. We're eventually headed here to build an internal combustion engine. Whether we do the gasoline Otto cycle, or whether we do the diesel cycle, or whether we do the rotary motor Rankine cycle, we're going to calculate what is the efficiency of these engines. Yeah. All right, well, at least in the few minutes I have left, let me just emphasize this here, is pressure then is defined as force per area. And I throw that on the board because everybody should have seen that in 102. However, some of you in 121 last semester, we didn't quite get to that chapter 14. In 14 we're talking more about pressure. But that's the definition of pressure. Pressure is force divided by area. So if I'm looking at the molecules in this gas, and these gases are pushing with a force on this piston, as I squish it down here, I can change this integral to say the work done on the gas, the work done on my system is equal to what? Well, I guess my first step would be to change the force to pressure times area times dx, where the pressure is the pressure of that gas. The area is the area pushing on that piston. So in this case, it's this circular cross-sectional area as I push this down. But what's nice about that is I just changed my equation from force to pressure. And pressure is then related to volume and temperature. And then I can look at how am I compressing my gas. In fact, I'll do you one better. And actually two better here. I got to change two things. I'll start with what's this? That's the volume change. And so as I am pushing this piston down, this becomes pressure and volume. So work, which is force times distance, really, is the same as pressure times volume. Okay, and so that's the work being done. One more little subtlety here, and I'll take your question, is we got to watch our sign real carefully here. This whole argument I've made has just been absolute values. Work is what? Wasn't it really force dot distance? Wasn't it a dot product so we could keep our sign correctly? Here's why I say that. Look carefully at what I have here. The distance is down. Which way is the force from the gas? Up. So this should really have a cosine of 180 degrees. If you're calculating the work on the gas using the pressure of the gas, the pressure is pushing out as the piston comes down. And so there should be a minus sign as we go from initial volume to final volume. And I'm going to put that over here. Here then becomes what I would call equation number 4, since I was doing accounting of the equations today, saying, look, the first 3 I have given you are calculating heat energies. Temperature changes or phase changes is the first half of this chapter. That's the review. I'm betting that nobody has done that equation yet, since it takes calculus, and this is the first calculus-based science class you had. But this is the energy based upon work, and it's based upon an integral. And maybe I should put initial volume to final volume. How much work is done? Now, let me emphasize it again. Doesn't it depend on how I compress my gas? In other words, back to this little mental picture here. Here's my gas, right? You already told me that if I were to, say, clamp this, actually, let me put a weight on it first, and then clamp it. If I were to warm it up, and this thing's about 80 degrees in here, Celsius. So sitting out in the room, it was about 20. I'm going to end up warming it from 20 to about 80. Okay. How much energy does it take to warm up to 80 degrees would be a different and a smaller number than, let me take it out. Let me cool it down real quick. I don't know if that's quite room temperature. Probably not. I'll do it again. If it goes up, oh, I want to leave the weight there. Sorry, if I loosen the clamp. Oh, I cooled it too much. But as I warm it now, I'm still going to warm it up to 80 degrees, right? I'm still going to warm it from 20 to 80. Does it take the same amount of energy to warm up? No. Why not? Because as I'm adding energy, some of the energy gets siphoned off, if you will, doing work. That could be a good thing if that's what we wanted to happen. It's a bad thing if we don't. Like I said, the example I gave was filling up a 5-gallon bucket that has a hole in it. You got to put 6 gallons of water in there to fill up a 5-gallon bucket because it leaked out. That's probably a bad thing because you probably don't want the bucket to leak. In this case, I probably want to lift something or make a car move, so the energy coming out is probably a good thing. But my point was back then, and it is now, is how you add the energy. Whether you add it at constant volume or constant pressure means we have to add different amounts of thermal energy. And likewise, I think you're seeing it here. If I were to compress this, according to this equation, this would calculate how much work is needed to compress this. But how you compress it is very important. For example, let's say that I compress this at constant temperature. Let's just say this was already sitting in the hot water. As I go to compress this, if it wasn't for the fact it's sitting in a container that can have heat come out and into the hot water, I would say it warms up. So even though this is starting at 80 degrees, as I squeeze it, as you saw here with this one, it would go up to 90, 100. And for me to squeeze it more and more and more is kind of hard. Not only because the volume gets smaller, but because the temperature is going to go up, right? Both of those contribute to a higher pressure. But on the other hand, if I were to squeeze this gas kind of slowly, while it's sitting in here, as I squeeze it, instead of the gas actually warming up, what would happen to that extra energy? It would be warming up the water, right? The gas inside would warm up to, say, 81, but then it would lose that heat. So as I'm compressing it, the temperature remains constant. And I claim that squeezing this down when the temperature remains constant is a little bit easier. Why? Because the pressure is only going to increase because of the volume change, not because of the temperature change. And so my point is, again, just like thermal energy, just like work energy, there's what we would call its path dependent. How did you squeeze the gas? And I claim that squeezing the gas when it is connected to a heat reservoir means its temperature will remain the same, and it would take less work than if I were to squeeze the gas and its temperature were to change. Does that make sense? Because if that thing starts to get warm inside, the pressure starts to build up, not just because the volume changed, but also because the temperature goes up. So, we are out of time. But we should look at all these calculations. What if the pressure is constant? What if the volume is constant? What if the